Imagine you're looking at a digital photograph on your phone. Maybe it's a high-resolution image of a really sharp horizon line, right, where the dark blue ocean meets a bright white sky.
Right, a really crisp contrast.
Yeah, exactly. And if you just look at the whole picture, it's a beautiful, crisp image. But imagine you start to zoom in, and I mean really zoom in,
You're pinching the screen over and over.
pushing past the clouds, past the individual waves, until you are looking at the exact microscopic boundary line between a single blue pixel and a single white pixel.
Oh, wow.
What actually happens in that infinitesimally small space between those two colors? Like, where does one state of reality end and another completely different state begin?
It's a great question.
Welcome to this deep dive. Today, we have a mission for you. We are going to unpack a really fascinating body of source material titled Day 12 Limits, Engineering, and Code.
And it is an incredibly rich look into the architecture of our modern world. I mean, our goal today is to take this seemingly abstract mathematical concept of limits.
Which is the foundational idea of calculus, right?
Exactly. We're going to see how those microscopic invisible boundaries actually govern the physical limits of the technology around you.
Yeah, we're talking about the aerospace engineering behind supersonic jets, the microscopic traces inside computer chips, and even the artificial intelligence that relies on these boundaries to actually learn.
Because it's so easy to dismiss pure math as just, chalkboard theory.
Oh, for sure. Just stuff you suffered through in high school.
Right. But as we'll see, those theories form the literal, invisible scaffolding of physical engineering. But before we can understand how this affects an F-16 fighter jet or an AI chatbot, we need to briefly ground ourselves in the pure mathematical rules of the road.
We have to establish what it actually means for a system to be mathematically continuous.
Right. So in the strictest mathematical terms, a function is continuous at a specific point, let's just call that point x equals c, if the function's actual value exactly matches what you'd expect it to be if you looked at all the points immediately adjacent to it.
Okay, makes sense.
But pure math is unforgiving. For a system to be truly continuous, it has to simultaneously pass three very rigid criteria. First, the point has to actually exist in the domain.
Meaning the function must be explicitly defined there.
Yes.
Because, you need a destination to begin with. You can't evaluate a coordinate that just leads to a blank space.
Exactly. You can't navigate to nowhere. Second, the mathematical limit must exist as x approaches that specific point c. And third, the limit you are approaching must perfectly equal the actual defined value of the function at that exact coordinate.
Right, and this is where the concept of directional convergence comes into play, isn't it?
Yes, it is.
Because you have to evaluate the approach from both directions. You have the left-hand limit coming from the negative side of the coordinate plane, and then the right-hand limit coming from the positive side.
And the existence of a true mathematical limit depends entirely on those two sides agreeing. The left-hand limit and the right-hand limit must converge to the exact same finite value.
If they do, the limit exists.
Right. But if they don't, the system breaks. You end up with discontinuities. And two specific types of breaks are really critical to understand here.
Okay, what are they?
First, you have a jump discontinuity. That's when the left-hand limit and the right-hand limit converge on completely different values.
Okay.
Second, you have a removable discontinuity.
Right.
That's when the left and right sides do match, like they point to the exact same numerical spot, but the actual value of the function at that spot is somewhere else entirely, or it's just missing.
I think we need to frame this structurally, something you can visualize without, staring at a graph.
Good idea.
Think about engineering a massive suspension bridge starting from two opposite shores. The left side of the bridge construction is your left-hand limit, and the right side is your right-hand limit.
I like this.
So a jump discontinuity is what happens when the two construction crews build out over the water, but when they meet in the middle, they discover a massive structural misalignment.
Oh, man.
Yeah, the left side is suddenly 20 feet higher than the right side. The two limits just do not line up.
Which is a catastrophic failure of planning.
Right. Now, a removable discontinuity is a different kind of failure. The two crews do their jobs perfectly. The left side and right side align flawlessly in the middle. The mathematical limit exists.
Right.
But the paving crew simply forgot to drop the final keystone into the very center block. The bridge aligns perfectly, but there is a single isolated void dropping straight down to the river right in the center.
And pure mathematics absolutely despises these broken bridges. Calculus demands smooth, predictable, differentiable curves to function.
But what's incredible about human engineering is that while pure math hates these discontinuities, engineers operating in the messy physical world actively exploit these broken bridges.
They absolutely do.
Because if pure math rejects a broken bridge, physics sometimes forces one to exist anyway. So let's transition from the chalkboard to the sky. Let's look at the first engineering domain where the physical world creates one of these massive mathematical jumps.
Supersonic flight.
Yes.
When an aircraft, like a fighter jet, accelerates from subsonic speeds to supersonic speeds, it crosses this profound physical boundary. The fluid properties of the air around the plane basically cannot adjust fast enough.
Say, sort of pile up.
Exactly. They change so rapidly that they form a normal shockwave. And across that shockwave, physical properties of the air, specifically the pressure, the density, and the flow velocity, they all experience a violent, near-instantaneous jump.
So aerospace engineers looking at the shockwave make a really fascinating decision. They model it as a literal mathematical discontinuity, a broken bridge.
Which seems counterintuitive, right?
Yeah. They treat the air immediately in front of the shockwave and the air immediately behind it as having completely different values that do not smoothly connect.
But by modeling it as a jump discontinuity, it actually allows them to utilize a specific set of physics equations called the Rankine-Hugoniot jump conditions.
The Rankine-Hugoniot jump conditions.
Yeah, and these equations are brilliant because they relate the states of the gas on both sides of the shockwave to conserve mass, momentum, and energy by treating the transition as having zero thickness.
Like a pure mathematical jump.
Exactly. It allows engineers to balance the forces across the boundary.
Wait, I have to push back on this a bit because there's a fascinating contradiction here between the math and the physical universe.
How so?
Well, microscopically, down at the level of individual air molecules, the universe is still perfectly continuous. Like, the nitrogen and oxygen molecules are still colliding smoothly. They don't just magically teleport from a low-pressure state to a high-pressure state without passing through the physical states in between.
That's true.
So why do aerospace engineers intentionally choose to pretend the math is broken? Because it makes solving the real-world problem easier.
It's entirely because of the scale of the problem. At the macroscopic scale, like the scale of an entire F-16 airframe moving at Mach 2, trying to calculate the smooth, continuous interaction of trillions of individual air molecules inside a transition zone that's only a fraction of a millimeter thick. It's computationally impossible.
That's just too complex.
Way too complex. So engineers evaluate the one-sided limits instead. They look at the left-hand limit of the air pressure just before the shockwaves and the right-hand limit of the air pressure just after it.
And because those two limits do not equal each other, they have their mathematical jump.
Right. And calculating the sheer size of that one-sided jump is what allows them to quantify the massive drag forces and structural load spikes that are about to slam into the wings. They mathematically isolate the discontinuity to ensure the plane has the structural integrity to survive crossing it.
That is wild.
So to our listener, the next time you hear the sharp crack of a sonic boom overhead, realize you are literally hearing a one-sided mathematical limit in action, keeping the plane from ripping apart.
Wow. So in aerospace, the physical reality forces a massive jump, and we use math to model it as a broken bridge just to survive it. But if we step down from the scale of fighter jets to the microscopic scale of computer chips, we encounter the exact inverse problem.
We really do.
Because in electronics, the math demands a perfect, instantaneous jump. But the physical reality of the universe absolutely refuses to allow it.
Because digital circuits, in a perfect theoretical world, operate entirely on binary states, zeros and ones, off and on. Mathematically, this perfect digital switch is modeled by something called the Heaviside step function.
Okay, how does that look?
Well, if you picture it on a graph, it looks exactly like a single perfect staircase step. You're riding along a flat line at 0 volts, and then instantly straight up a vertical wall to a flat line at 5 volts.
But evaluating the limit at that vertical wall creates a massive problem for physical engineering.
Oh, a huge problem.
Because if you have an ideal switch that turns on at exactly time 0, the left-hand limit, like at the microsecond before you hit the switch, is 0 volts.
Right.
The right-hand limit, the microsecond after, is 5 volts. Because the jump is instantaneous, the limit simply does not exist. In calculus terms, the derivative, which is the rate of change with respect to time, is infinite. It's an infinite slew rate. The notation is dv over dt equals infinity.
And the physical universe does not tolerate infinity. You simply cannot have an infinite instantaneous jump of energy in a physical copper wire. The engineering reality is that physical circuits are messy.
Very messy.
The traces on a microchip possess what engineers call parasitic capacitance and resistance.
I've always loved that term, parasitic. It's as if the physical wires themselves are leaching away the perfection of the mathematical model.
That's exactly what they're doing.
So if we think of an analogy, it's kind of like turning on a faucet, right? The math says the water instantly hits full glass the millisecond you turn the handle, but physics says it takes a fraction of a second for the water pressure to build up.
Yes, excellent analogy. Instead of an instant jump, the electromagnetic field inside the wire possesses a kind of physical inertia. It takes time for the electrons to charge up those parasitic capacitors.
And those fractions of a second are what hardware engineers agonize over so your devices don't crash?
Right. And that physical inertia is modeled by a very specific voltage profile equation. It's V of t equals V, 0 times 1 minus e to the power of negative t over RC.
Where R is resistance and C is capacitance.
Got it. What this equation describes is reality fighting back against the instant change. The physical world smooths out the sudden, impossible vertical wall of the Heaviside step function into a continuous differentiable curve.
It forces the broken bridge to physically connect.
Exactly.
And electronics engineers actually rely heavily on this smoothed out curve, don't they? They evaluate the mathematical limit of that voltage as time goes to infinity.
They have to. They have to. In order to establish the most crucial parameters of a microchip, they're analyzing that curve to establish clock cycles, setup times, and propagation delays.
Right.
Because by understanding exactly how the physical wire smooths out the binary jump, they can mitigate signal integrity failures. Like if a computer's processor tries to read a 1 or a 0 while the voltage is still slowly climbing up that smoothed out transient curve, the system misinterprets the data.
The processor expects a 1, but reads a 0 because the voltage hasn't arrived yet and the whole system crashes.
Exactly.
So those tiny fractions of a nanosecond while the voltage is ramping up along that continuous curve are the critical windows hardware engineers agonize over to keep our devices stable.
They are actively managing the unavoidable transition between pure mathematical theory and messy physical reality.
Okay, so we've seen how physical wires force perfect math to smooth out. But the hardware isn't the only domain dealing with this limit problem. The software running on top of those very chips, specifically deep learning AI, has to actively engineer its own mathematical smoothness, or it completely fails to function.
Yeah, this brings us to the intersection of computing and software engineering, specifically focusing on how neural networks learn through gradient descent.
Right, because for an AI to learn, whether it's a large language model processing text or a vision model identifying tumors in an X-ray, it uses an optimization process called gradient descent to minimize its errors or its loss.
And you can visualize gradient descent like trying to find the absolute bottom of a complex, multidimensional valley while blindfolded.
I love that image.
You feel the slope of the ground under your feet, and you take a step downhill. In calculus, that slope you're feeling is the derivative.
But the limit problem almost killed early artificial intelligence.
It really did.
Early neural networks tried to operate just like those ideal electronic switches we were discussing. They used a binary step function as their activation function. An artificial neuron was either completely off or completely on, 0 or 1.
A literal jump discontinuity inside the software.
Exactly. And the consequence of that flat line is fatal for learning. Because the function is a flat horizontal line at 0, an instantaneous vertical jump, and then a flat horizontal line at 1. The derivative, the slope of the ground, is exactly 0 everywhere except the exact threshold of the jump, where it is completely undefined.
So basically, if the AI hits a mathematical jump discontinuity, it goes entirely blind.
Yes.
It needs that smoothed out slope to know which way is downhill to learn.
Exactly. If the derivative is 0, the AI can't feel any slope. It's standing on perfectly flat ground, blindfolded, with no idea which way is downhill.
So gradient descent completely breaks down, because the mathematical mechanism behind AI learning is the chain rule in calculus, utilized in a process called backpropagation.
Right.
The network calculates the error at the output and then multiplies the gradients backward through the layers of the network to update the weights. But if you multiply by a derivative of 0, the gradient vanishes entirely.
The error signal stops dead.
The network cannot update its weights.
So how did computer scientists build a bridge over that mathematical void? Like, How did they fix the limit problem?
Well, they saved modern AI by entirely abandoning those rigid perfect step functions. They replaced them with continuous differentiable approximations.
They artificially engineered a slope into the jump.
Exactly. One of the most famous examples and the backbone of a lot of modern deep learning is the rectified linear unit, or ReLU.
ReLU is such an elegant solution. The function is simply the maximum of 0 or x, so for any negative number, the output is just 0, a flat line.
Right.
But the moment x becomes positive, the output is just x. It turns that vertical cliff into a gentle, steady 45-degree hill.
And that steady hill provides a constant derivative of 1 for all positive inputs. That constant slope allows the error signals to flow backward perfectly across hundreds of layers of a neural network without vanishing to 0 or exploding into infinity.
Oh, wow.
Yeah, and engineers also use smooth transcendental functions like the sigmoid function or GLU, the Gaussian error linear unit, depending on the specific architecture. By evaluating the limits of these continuous functions, they ensure that there are no broken mathematical bridges blocking the backpropagation.
So without artificially smoothing out the curve, modern AI architectures simply wouldn't work.
They wouldn't be able to learn at all.
That is incredible. We've gone from jets to chips to AI. We've traced this concept from the violent shockwaves tearing over supersonic jets to the parasitic inertia smoothing out microchips to the artificial slopes that allow neural networks to think.
It's remarkable how this one mathematical boundary scales across physical reality.
It really is. But to wrap up, how do engineers actually study and compare these smooth curves versus mathematical jumps in the real world, like day to day?
They rely on code, and the source material provides a brilliant practical implementation of this at the very end, utilizing a Python script to study these exact boundaries.
Yeah, the script uses a dual approach that beautifully illustrates this tension between pure math and physical engineering. It starts with a library called SIMPy for standalone symbolic analysis.
SIMPy handles the pure unbroken theory.
Right. SIMPy is used to evaluate the analytical exact mathematical limits of a continuous linear function versus a discontinuous piecewise step function.
It isn't calculating decimals or floating point approximations. It manipulates the algebraic symbols themselves. It calculates the theoretical limit as x approaches a specific boundary coordinate, which the code defines as x equals 2.
It's looking for the perfect exact answer in a pristine mathematical vacuum.
Exactly.
But then the script pivots. It brings in two completely different tools, NumPy and Matplotlib. NumPy doesn't do symbolic purity. It evaluates discrete floating point approximations. It approaches the boundary at x equals 2 by calculating discrete numerical steps.
Like 1.99, then 1.999, then 2.001.
Yes. It maps the real-world numerical approximation of the space. And then Matplotlib is used to visually contrast how the two structures actually behave. It visualizes the data, showing the continuous line versus the broken jump.
It's such a perfect encapsulation of everything we've unpacked today.
I marvel at this dual approach. I mean, we use SIMPy to look at the perfect, pure math of the bridge, the ideal, flawless design in the architect's head. And then we use NumPy and Matplotlib to draw the real-world picture, see exactly what the gap looks like to the human eye.
You absolutely have to understand the pure, unbroken mathematical theory, but you also have to be armed with the numerical tools to engineer around the messy, broken physical reality.
Okay, so let's summarize this journey for you, the listener. The next time you encounter the concept of mathematical limits evaluating what happens as x approaches c, remember that they aren't just abstract torture mechanisms invented for calculus exams.
They really aren't.
They are the actual, tangible boundary lines used to manage shockwaves in supersonic jets, stabilize the fragile voltage in our microchips, and allow neural networks to learn. The math gives us the language to define the boundaries of the physical universe, and engineering gives us the tools to crock them.
Before we wrap up, investigating all these different domains leaves us with one final, unexplored idea to ponder.
Oh, lay it on me.
We've spent this entire time analyzing how engineers are constantly forced to smooth out binary jumps. If human engineers constantly have to invent smooth, continuous functions, like implementing ReLU in artificial intelligence, or relying on RC transients to smooth out voltage spikes in electronics, just to bridge the gap between ideal mathematical jumps and physical reality.
Yeah.
Does that imply the universe itself fundamentally rejects true, instantaneous binary changes? And if so, are we chasing an impossible, unnatural illusion every time we try to perfectly digitize our beautifully continuous analog world into simple ones and zeros?
Wow. Something for you to mull over the next time you zoom in on a digital photo, searching for the impossible space between the pixels. Thank you for joining us on this deep dive. We'll catch you on the next one.